Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and or questions, drop them in the comment section below or write to us info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
Hello everyone, welcome and thank you for joining us for today's Oxygen Talk, brought to you by the Oxygen Alliance. My name is Chaponda, a biomedical engineer for the Oxygen Alliance, and I'm excited to be your host today. The Oxygen Talk is a virtual meeting where we discuss various topics related to medical oxygen. I am hosting this call from Lilongwe, Malawi, and I would love to know where you're joining us from. So feel free to type your name and your location in the chat. And if you'd also like to be added to the emailing list, make sure you drop your email in the chat as well. Today we have a very informative presentation brought to you by the OpenO2 engineers on the factors that contribute to low oxygen purity in an oxygen concentrator. Today our presenters are John Kabambe, Sungeni Gonjani, Foster Sentala, and Jen Chaponda. I'm excited that we have you today, and I encourage you to take some notes as we look forward to hearing your comments and your questions at the end of the presentation. So without taking much of your time, let me hand the floor over to John Kabambe. So John, over to you.
Hi, thank you, Aubrey. Good afternoon, everyone. As already introduced, my name is John Kabambe, a biomedical engineer with the Global Health Informatics Institute under the OpenO2 initiative. And today we'll be having an exciting topic known as factors that contribute to low oxygen purity in an oxygen concentrator. This presentation is going to cover the introduction to low purity in oxygen concentrators, as well as the pressure swing adsorption technology, environmental, user, and machine factors that lead to low purity in oxygen concentrators. Now, when we say low oxygen purity in an oxygen concentrator, it refers to the situation when the percentage of oxygen in the output gas produced by the oxygen concentrator is lower than the expected or required level. And according to the World Health Organization, oxygen concentrators should deliver an oxygen concentration, also referred to as oxygen purity, of not less than 82% when the machine is working normally. And the illustration to the right shows an oxygen concentrator giving an oxygen purity of 27.8%, which is below the stated standard. Now, when the oxygen purity is low, it means that the device is not able to separate oxygen from other gases in the air as efficiently as it should. This can impact the effectiveness of the treatment for patients who rely on a specific concentration of oxygen for their health conditions. Now, let us look at why exactly it is important to discuss this topic. Well, firstly, let's consider patient safety. Low oxygen purity can be harmful, especially for patients who rely on a specific concentration of oxygen for their health condition. And understanding these factors can help prevent these health risks. Secondly, moving to device efficiency. Knowing what affects the oxygen purity can help in maintaining the efficiency of the device. Regular maintenance and checks can ensure the concentrator is working at its optimal level. And in terms of emergency preparedness, understanding these factors can ensure the concentrator provides the necessary oxygen purity when it is most needed. And lastly, discussing these factors can lead to innovation and improvement in the design and functionality of oxygen concentrators, making them more reliable and more efficient. Now let us appreciate some of the oxygen generation devices and technologies that exist today. We have the oxygen concentrators, which I mentioned earlier. We have the pressure swing adsorption oxygen plants, the liquid oxygen, as well as water electrolyzers. There are various devices and technologies used for oxygen generation, but our primary focus today will be on oxygen concentrators, which are widely used due to their efficiency and convenience. Now, what exactly are oxygen concentrators? These are medical devices that produce concentrated medical grade oxygen from ambient air. They do this by separating nitrogen and other trace gases from the air. An oxygen concentrator operates on the principle of pressure swing adsorption using a microporous granulated molecular sieve material called zeolite. Now let us dive deep into this PSA technology. It is basically used for selective adsorption of nitrogen from air under high pressure, hence producing high oxygen concentration as the output. Pressure swing adsorption in oxygen concentrators involves several steps, and the first step is adsorption. Here, the ambient air is compressed to high pressures of typically about 20 psi. This pressure allows the zeolite to effectively capture nitrogen molecules, letting oxygen to flow through. And moving to the next step, we have desorption. Once the sieve bed reaches nitrogen saturation, the pressure is reduced to around 14 psi. This decrease in pressure releases the trapped nitrogen, rejuvenating the sieve bed for the next cycle. And here you can notice the pressure swing comes into play. The constant pressurizing and depressurizing of the sieve bed is what defines the pressure swing process. And the fifth step, we have oxygen enrichment. The remaining oxygen-rich gas from each sieve bed is collected and it becomes ready for use. The oxygen produced typically has a concentration of up to 95% oxygen. The sixth and final step is alternating beds for continuous oxygen supply. In an oxygen concentrator system, we have two beds which are filled with zeolite. And while one bed is in adsorption phase, trapping nitrogen and enriching oxygen, the other bed is simultaneously in the desorption phase, releasing trapped nitrogen and preparing for the next cycle. And this alternation between adsorption and desorption phase of the two beds is what ensures a continuous flow of oxygen. And the synchronized switching guarantees that there's always at least one bed that is actively producing oxygen while the other regenerates. Now, moving on, the diagram on the presentation shows most of the parts of a typical oxygen concentrator, and I will use the diagram to explain more on how an oxygen concentrator works. We will start on the top left side where it says ambient air and finish on the bottom right side where it says to patient. So please follow as I explain each step. The operation process begins with the ambient air, as I've mentioned. This ambient air is in the room and it is a mixture of 78% nitrogen, 21% oxygen, and 1% of other trace gases. This air is drawn into the oxygen concentrator by the cabinet fan and the compressor. And upon entering, the air first passes through an intake air filter that removes large dust particles and other impurities. The filtered air subsequently enters the intake resonator, and this serves the purpose of reducing the noise that is produced during the intake process. Following this, the air is compressed by the air compressor. This increases its pressure and prepares it for the next stage. And you may notice that the compressor is also attached to a run capacitor. The run capacitor aids the compressor's operation by storing and releasing electrical energy during each cycle of compression. And meanwhile, the control circuit board, the part that is in green, regulates the electrical components of the concentrator, ensuring they work in harmony. And the compressed air is then directed into one of the sieve beds by either a solenoid valve or a rotary valve, depending on the design and model of the oxygen concentrator. These valves basically control the flow of air into and out of the sieve beds. And as the sieve beds fill with nitrogen, the exhaust muffler quietly releases the nitrogen back into the room. Inside the sieve beds, there's a material known as zeolite, as I've already mentioned, that absorbs nitrogen from the air, increasing the concentration of oxygen in the remaining gas. And we have the equalization valve. This balances the pressure between the two sieve beds during the switchover phase. And then from there, we have the production of oxygen-enriched gas, and this oxygen-enriched gas is then stored in the product tank. We have a pressure regulator that ensures that the oxygen is delivered at a safe and consistent pressure to the patient. And we also have an oxygen sensor. This monitors the concentration of oxygen in the output gas and triggers an alarm if the concentration drops below a certain level. And before the oxygen is delivered to the patient, it passes through a bacteria filter, which removes any remaining impurities. And from there, we have the flow meter that allows the user or healthcare provider to adjust the flow rate of the oxygen, ensuring that the patient is receiving the correct amount. And the next part is the humidification of oxygen. We have a humidifier bottle. This is where the purified and concentrated oxygen may pass through, and it basically adds moisture to the oxygen. This helps to prevent dryness and irritation in the patient's airway as they're being treated using the oxygen concentrator. And finally, the purified and concentrated oxygen is delivered to the patient through the oxygen outlet. So this entire process is cyclical and continues for as long as the oxygen concentrator is powered on and functioning correctly. It's a complex system, but each component that I've mentioned plays a crucial role in ensuring the delivery of high purity oxygen to the patient. So reaching this far, I would like to hand over the presentation to my colleague Sungeni to proceed.
Thank you so much, John Kabambe. My name is Sungeni Gonjani, and I'm a biomedical engineering intern from the Open O2. I will take you through the environmental factors that affect oxygen generation, which are temperature, humidity, air quality, and power supply system. To begin with, temperature is one of the environmental factors that affect oxygen generation. Extreme temperatures above 40 degrees Celsius in the room can lead to overheating of the compressor. Hence, the compressor can break down or it can just shut down. This can lead to inefficiency. And on the other hand, lower temperatures are efficient to operate a concentrator in, since it helps in increasing oxygen purity. The problem of high temperatures can be resolved by placing the oxygen concentrators in rooms with stable temperatures, like room temperatures, which are from 20 degrees Celsius to 24 degrees Celsius. And also making sure that the fans placed in the concentrators are working. Also make sure that the vents are able to allow air to come out of the concentrator. The second environmental factor that can affect oxygen generation is humidity. Zeolite materials in the seed beds have high affinity for moisture. Hence, once the ambient air has high moisture content in it, the moisture is most likely to stick to the pores of the zeolite material, hence inhibiting nitrogen adsorption. This will eventually lead to low oxygen purity. This problem can be solved by operating the concentrator in a well-ventilated room, so that there is a very great circulation that will ensure that there will be no buildup of moisture that can affect the adsorption process. The third environmental factor that can affect oxygen generation is through air quality of ambient air. Dust and other pollutants in the air can lead to low oxygen purity when they have entered the air system. This can be done when the filters are being filled by dust to an extent that they cannot filter effectively. This problem can be fixed by making sure that the concentrators have clean filters incorporated all the time, so that it filters the air entering the concentrator, and also make sure that the walls are clean always. Finally, power stability is the other environmental factor that can affect oxygen generation. Oxygen concentrators require a stable power supply, and hence low voltages can lead to the disruption of the oxygen production process, and hence lead to inconsistent output. This can be overcome by consulting the electrician once the problem has been observed. And if it persists, contacting the power supplier is a very good option. Backup power source is also always needed so that the production will continue, even if the main power supply is off. Reaching this juncture, let me leave the floor to my colleague, Jen Chaponda. Over to you, Jen.
Thank you so much, Sungen, for that informative presentation. Indeed, my name is Jen Chaponda. I'm a biomedical engineer under the Open O2 initiative. In this presentation, I will take you through the user factors that contribute to low oxygen purity in an oxygen concentrator, and also the best practices in order to address these factors. The first user factor is improper placement of an oxygen concentrator. So improper placement of an oxygen concentrator can greatly affect the performance of the oxygen concentrator, thereby reducing the purity of oxygen being produced. And improper placement of an oxygen concentrator involves placing the oxygen concentrator in an area with poor ventilation. And this can hinder the intake of ambient air that is necessary for oxygen production. Without proper airflow, the oxygen concentrator may struggle to draw in sufficient air in order to produce the required oxygen purity. An example can be placing the oxygen concentrator in a room with windows closed. The lack of fresh air circulation in such a room can affect the oxygen concentrator's ability to take air efficiently, resulting in decreased oxygen purity. Another thing is blocking the air intakes. So blocking the air intakes of the oxygen concentrator with objects or obstructions can restrict the flow of air into the unit. And this reduces the amount of ambient air available for oxygen extraction, leading to decreased oxygen purity. An example can be placing the device against a wall or furniture, as this can block the air intake filters. Similarly, covering the filters with fabric, with papers or other items can obstruct the airflow and impact purity of the produced oxygen. Another thing is placing the oxygen concentrator close to a wall. So positioning an oxygen concentrator too close to a wall can trap the heat it generates. And this can make the area around the oxygen concentrator hot, especially if the wall blocks proper airflow. The increased heat might result to overheating of the oxygen concentrator, and this could affect the purity of the oxygen that is being produced. So in order to overcome all this, the user needs to follow the following best practices when using the oxygen concentrator on a patient. Firstly, the user should position the oxygen concentrator in an open area with adequate space around it in order to allow proper airflow. And also avoid placing the oxygen concentrator in confined spaces or in areas with restricted ventilation, such as under the bed or in a room with closed windows. The user should also ensure that the air intake filters of the oxygen concentrator are not obstructed by any objects, and should keep the area around the oxygen concentrator clear of obstacles in order to allow unrestricted airflow into the unit. The user should also make sure to press the oxygen concentrator so that all sides are at least 30 centimeters away from walls, furniture, and the like, in order to prevent the unit from overheating. Moving on, another user factor is incorrect flow meter settings. So setting the flow meter of an oxygen concentrator above the maximum recommended flow rate decreases the purity of the oxygen produced by an oxygen concentrator. On your left-hand side is a graph showing oxygen concentration against flow rate for a 5-liter oxygen concentrator. It's just an example showing what happens to oxygen purity when you increase the flow rate. So you can see that the purity is 95.6% from 1 liters per minute to 5 liters per minute. But it starts to decrease as the flow rate exceeds 5 liters per minute. So this happens because as the flow rate increases, there is less time for the oxygen concentrator to separate oxygen from other gases in the air. So the oxygen concentrator needs time to effectively extract oxygen molecules from the surrounding air and concentrate them for delivery. And when the flow rate is increased, the oxygen concentrator may not be able to keep up with this process, resulting in a lower concentration of oxygen in the delivered air. Therefore, while increasing the flow rate may provide more oxygen per minute, it can reduce the overall purity of the oxygen being delivered. On your right-hand side is a flow meter for a 5-liter oxygen concentrator. As I've already said, the maximum recommended flow rate for such an oxygen concentrator is 5 liters per minute. So setting the flow meter above 5 liters per minute, that is up to the red line, will decrease the oxygen purity. So a user needs to always make sure that the flow meter bore on the flow meter does not exceed the maximum recommended flow rate of the oxygen concentrator. And in a case where there are 2 flow meters on a single oxygen concentrator, although both oxygen flow meters on an oxygen concentrator are calibrated to the maximum capacity of the machine and can be used simultaneously, the maximum flow rate at which the device can produce oxygen with recommended purity remains constant. For example, on a 10-liter oxygen concentrator, a user can set one flow meter at 6 liters per minute and the other at 2 liters per minute, making a total of 8 liters per minute. But it's not supposed to set one flow meter at 6 liters per minute and the other at 8 liters per minute, making a total of 14 liters per minute. So this is because if the combined flow rate exceeds the maximum capacity of the oxygen concentrator, the produced oxygen purity is affected. Moving on, another user factor is neglecting cleaning. So dust and other particles can accumulate on the air intake filters over time, reducing the efficiency of the oxygen concentrator. And a blocked humidifier bottle can affect the flow of air through the oxygen delivery system, affecting oxygen purity. Additionally, if the humidifier bottle is not clean and free of impurities, it can introduce contaminants into the airflow, further lowering oxygen purity. And also not reporting any strange behaviors on the oxygen concentrator to the maintenance department might lead to providing oxygen to patients that isn't as reliable or as safe as it should be. As such, the user needs to be cleaning the gross particle filter regularly with soap and water and allow it to dry in shady places. The user should also regularly inspect the humidifier bottle for any signs of blockage and also be cleaning the humidifier bottle with soap and water and allow it to dry completely and be changing the water in the humidifier bottle on a daily basis in order to prevent the building up of contaminants. And also the user should make it a habit to be reporting to the maintenance department on any unusual behaviors or alarms on the oxygen concentrator. Lastly, learning multiple appliances or devices on the same extension cord as the oxygen concentrator contributes to low oxygen purity, as it can lead to power fluctuations or overloading, affecting its performance. So when you plug multiple appliances into the same extension cord as the oxygen concentrator, as you can see on picture A, they will all share the same electrical power source. And this can be too much for the extension cord to handle, causing power fluctuations or overloading. So these fluctuations can affect the stability of the electrical power supplied to the oxygen concentrator. And this instability can disrupt how the concentrator works and making it harder for it to produce oxygen at the right purity levels. So in order to avoid this, the oxygen concentrator needs to be plugged directly into an electrical wall outlet, as you can see on picture B. Reaching this far, I will leave the floor to my colleague Foster Sentala to continue with the presentation. Over to you, Foster.
Thank you very much, my colleagues John, Sungeni, and Jen, for your wonderful presentation. My name is Foster Sentala, and I'm a biomedical engineer for the Oxygen Alliance. And I'll be taking you through the last part of our presentation today, which is covering the machine factors that also contribute to low oxygen purity generated from an oxygen concentrator. So by definition, machine factors are usually the hardware factors that affect the general performance of oxygen concentrators. And in my presentation, I'll cover leakages, kinks and blockages, sievebed check valves, feed waste control valves, used zeolite in sievebeds, worn-out compressor kits, defective printed circuit boards, pressure regulators, and finally, I will talk on cooling cabinet fan. So the first factor that I will cover today are leakages, kinks, and blockages. So wherever there are leakages in the system, this directly affects the pressure swing adsorption process by increasing the flow and also reducing pressure. So as it was covered by John, the pressure swing adsorption entirely depends on pressure building up process. So whenever there is a factor that is affecting pressure in the system, you are directly reducing purity of oxygen. So the different models of concentrators that we have use different set values of pressure for the adsorption process. So other models use a range of 20 to 30 psis, and in other machine models, it can be less or greater than 20 or 30. So wherever you have a leakage in the system, you are increasing the flow of gas in the system. So instead of having the gas flowing in the pipes, you have the gas flowing out through the leakages. So the pressure drops, and that affects the adsorption process. The other factor that also affects purity are the kinks and blockages. If you can see in the graphics, there is a pipe that is being pressed against by a sieve bed and the cabinet. So that is blocking the path of air, and that can reduce oxygen purity because it is affecting the flow of the gas. So wherever you have kinks and blockages, you have an obstruction to flow. So you have less air reaching the sieve beds, and you have less pressure being built in the system. And that reduces the purity of the oxygen that is being generated by the oxygen concentrator. So despite the kinks, one major factor that introduces blockages in the system is improper care of air filters. So as Jen already presented, you always need to keep the filters clean, and also you need to replace the filters over time so that you have a good flow of air into your system. So in cases whereby there is a blockage, there is a check that you can use to know that there is a blockage in the system. So usually this triggers a safety relief valve on the air compressor to pop up to release the excessive pressure that is being built. So whenever you realize that the valve, the safety relief valve that is located on the air compressor keeps opening, then you need to check whether there are blockages in the system. So to fix this, the leakages, the kinks, and the blockages, an easy fix for the leaks, you need to do a leak test, which we use a certified leak detection solution. So you can use soapy water foam, and you apply to all areas of potential leakage. So whenever there is a leakage, you will see bubbles coming out from the leakage point, and then you know there is a leakage. Then using one of the following tools that are indicated in these pictures, either the push to connect tube fittings or the stainless steel hose clamps or the zip ties, then you can use to secure a tight fit or where you have pipes joining. And in this way, you can reduce leakages. For the blockages, you just need to check your pipes and the connections, and then you see where there is a blockage, and then you need to get rid of the blockages. Moving on, we'll discuss the seatbelt check valves. So these are one-way valves that are placed between the accumulator tank and the outlet of the seatbeds. So their function are to prevent reverse flow of oxygen from the accumulator tank going back to the seatbeds. So whenever these one-way valves are not closing fully, then you have a reduction in the accumulator tank pressure. So remember, I said that when the pressure is decreasing, then you are directly affecting the ESA process. So you need to make sure that these valves are working fine so that you are achieving greater pressures that are recommended for the PSA process. So to deal with this, firstly, you need to perform accumulator pressure tests using a pressure gauge that you connect from a testing point on the accumulator tank. And then if you observe that the pressures that you're getting on the gauge are relatively lower than the specified values or on the specification sheet, then you need to replace the 40 valves. So to do that, you just disconnect the pipes from both ends of the valve, and then you replace with a new one. But always make sure that when you're replacing the valve, the outlet end is always facing the direction towards the accumulator tank, because you don't want to block air from the other side of the valve, because remember, this is a one-way valve. So make sure that the gas is flowing from the sieve beds towards the accumulator tank. Next, let us look at the feed waste control valves. And these are valves that are placed in the concentrator just to control the opening and closing, just to control the feeding and wasting operations of the sieve beds. So different machines use different control valves. Other machines use the rotary valve, as indicated on the picture on the left, and other machines use the solenoid valves, power solenoid valves, as also indicated in the other picture. So these valves are controlled by the printed circuit board, either through timings or sometimes through monitoring their pressure, the pressure in the sieve beds. So abnormal opening of the valves may result in the oxygen concentrator overpressurizing one sieve bed while leaving the other sieve bed in the resting mode. So this is mostly accompanied by the safety relief valve on the air compressor also opening up, because the system wants to get rid of the excess pressure. So whenever these valves are not operating fine, then you have overpressurization happening, and also the valve on the air compressor continuously opening. So the oxygen concentrator looks as if it is running on one sieve bed, and the purity drastically falls. So to get rid of this, you need to do a pressure test on the outlet of the sieve beds, and then you observe unit cycling. And if you see that one sieve bed is getting higher pressures than the other, then you know that the valves are not opening equally for the unit cycling process. So you need to make sure that the pressures are even, then you know that the valves are opening fine. So to check this, you can either check the voltage that are supplying the valves. So you disconnect the cable that is going to the valve, and then you measure the voltage on the PCBs. If you're getting uniform voltages as indicated in the operation manual, the service manual, then you need to check the valve itself. So for the solenoid valves, you either check for magnetization. So if the solenoids are magnetizing okay, then you know that it can be something else. So you either dismantle the valve, you disassemble it, you clean, and you reassemble it back to the oxygen concentrator. So if that does not help, then you might need to consider changing the whole valve unit. Next, I'll talk about zeolite that is found in pairs of sieve beds. So as John already talked about this is a material that the oxygen concentrator uses to filter the air, to remove the nitrogen, and then allow oxygen to pass through. So whenever this sieve material has been contaminated with moisture, mainly due to running the concentrator over time, thousands of hours, the zeolite tends to degrade. So as you can see on the picture, this is zeolite the zeolite that you see in the bag was collected from one concentrator and then was regenerated. So the water you see in the bottle actually came from the sieve material that is in the bag. So you might see that close to 500 mils was collected from the sieve material of one oxygen concentrator. So over time, the sieve material gets to accumulate this moisture when you're running the concentrator. So you need to also check the sieve material that it is pure and that it is performing quite okay. So there are several solutions that you can fix the problem of zeolite in oxygen concentrators, of which one of them is just to replace the whole pair of sieve beds in the concentrator with new sieve beds. Or if you don't have new sieve beds, then you can consider just purchasing sieve material from a manufacturer, and then you open up the sieve beds and you replace the sieve material with new zeolite. The third solution is regeneration. So we also did a talk on zeolite regeneration. You can go back to our YouTube channel and watch the whole talk. We did a whole talk on zeolite regeneration. So in simple terms, regenerating zeolite is just exposing the zeolite to excessive temperatures. So these are temperatures above 500 degrees Celsius, just to get rid of the water that is accumulated in the sieve material. So with these three solutions, you can deal with the problem of degraded zeolite in sieve beds. And after doing this, you should get improved oxygen purity from your oxygen concentrator. Next, we'll also look at another factor that also greatly affects oxygen purity in oxygen concentrators. And these are worn-out compressor kits. So remember, one of the essential parts of an oxygen concentrator is the air compressor. And inside the air compressor, this is where you have the sleeves, the capsules, the piston, and the cap retainer. So over time, over several hours of use of the oxygen concentrator, the capsules get to worn out, and even the sleeves, as you can see in the graphics. So the letter A indicates new capsule and new sleeve, while B, those are used up sleeve and capsule. So over time, you need to replace these capsules and the sleeves for you to have an efficiently running air compressor. So if these capsules and the sleeves are worn out, the pressure that you are realizing in the sieve beds and the accumulator pressure gets to reduce. So you always need to check whether the compressor is producing enough pressure. So you can do that by performing accumulator pressure test, or you can actually connect a pressure gauge at the outlet of the air compressor, and then you check the value and you compare on what is indicated in the specification sheet of that particular air compressor. If the values are not matching, then you might consider checking the capsules and the sleeves. A common way that you can also use to check if the air compressor is working fine is just to listen for a squeaking sound. So since the capsules are sealing the cap retainer and the sleeves, when they're worn out, there's too much noise coming from the air compressor. So if you're getting a squeaking sound from your air compressor, then you know that the capsules and the sleeves are worn out and you need to replace. So that is one way of fixing a compressor that is not working effectively. The other factor that we also discussed today are the defective printed circuit boards. So the general purpose of having a PCB in the oxygen concentrator is just to monitor and control all the components that are connected to the oxygen concentrator. And the components might be the valve, the control valve, the oxygen sensor, the pressure sensors, the LEDs, the alarms and everything, and all the other electrical components that you have inside the oxygen concentrator. So one important function of the PCB is to control the timed opening and closing of the feed waste valve. So whenever the unit cycling is affected by a defective board, whether due to a defective the pressure sensor on the board, then you have disrupted cycling in the oxygen concentrator. So whenever the opening and closing of the valve is affected, then you have maybe one seabed being pressurizing fully while the other one is not pressurizing fully. So you have a reduction in the oxygen purity. So you always need to replace all the further components of the board to make sure that you are having higher concentrations of oxygen coming from the oxygen concentrator. So one common problem that we have experienced working with one type of oxygen concentrator is a clocked sensor. So if you can see in the image, that is an oxygen sensor that is embedded on a board for an oxygen concentrator. And it usually develops clocks. I don't know if you can see from the picture where the arrow is pointing that there is a clock, a huge clock on the sensor. So these clocks usually introduce leakages in the system, and then that affects the pressure building process in the whole system. And you know, wherever you're having low pressures, then the PSA process is greatly affected, and you start to get lower purities of oxygen from the concentrator. So to solve these problems on the PCBs, you need to make sure that all the components on the board are working fine. So replace all the 40 components, all the sensors, the 40 or damaged cables, maybe the cables that are supplying the voltage to the valve. You always need to make sure that they are working fine. So if you have replaced all these components and you see that the compressor is not functioning as expected, then you might also consider just replacing the photo board with a new PCB. The other factor that we also discussed today is the pressure regulator. So this is placed on top of the accumulator tank. So it sits between the accumulator tank and the patient outlet port. So its function is basically to reduce the pressure, the PSA pressure, from approximately 25 psi to the patient pressure, which is usually 8.5 psi. So in cases whereby this pressure regulator is not functioning well, then you have a reduction in the PSA pressure. For example, if the pressure is not being reduced to 8.5 psi, then you have increased flow in the system. So instead of you building pressure in the seabeds and the accumulator tank, you have a continuous flow out of the system, and the PSA process is affected. So you need to make sure that this pressure regulator is functioning okay. So there is 2 ways that you can use to fix the problem with pressure regulators. One way is just to adjust the screw that is placed on the pressure regulator. So this screw actually adjusts the level of pressure that you are getting on the other end of the system. So if you're getting higher pressures, you need to adjust this screw on the pressure regulator, and then you set it to a level that is recommended. Other machines usually come with LEDs that indicate whether the system is getting low pressures or high pressures. So you might need to work with this screw to adjust the pressure to the recommended level. And if that does not solve the problem, then the other fix can be just replacing the 4-day pressure regulator with a new recommended pressure gauge, pressure regulator. The last factor that we'll discuss today are the cooling fans. So Sungeni, when she was presenting on the one environmental factor, which is temperature, she also mentioned about the compressors having a cooling fan inside their unit. So the basic function of the fan inside the concentrator is to provide a constant airflow to cool down the air compressor. So In cases whereby these fans are defective, then the internal temperature of the concentrator gets to rise up, and the compressors usually come with an internal thermoprotective device that is activated with high temperatures. And when they're activated, they shut down the whole compressor. So remember, the PSA process is a continuous production of oxygenated air. So wherever you have the compressor shut down, then you know the PSA process stops, and that should drastically reduce the purity of the oxygen that you're getting from the outlet port. So always make sure that these fans are working fine. So there are cases whereby maybe an engineer is trying to fix some part of the concentrator, and then before doing that, he or she removed the fan. And when you're replacing the fan, you might change the direction of the fan. So make sure that when you are assembling back the unit, you should make sure that the fan is always pointing or is always blowing towards the direction where you have the air compressor. So there's a picture on this slide. So if you can see from the arrow is pointing at a broken fan blade. So with time, with several hours of using the machine, you sometime might get some of the blades on the fan getting damaged, as you can see in the picture. So this can also lead to the concentrator producing a lot of noise. So when you have a lot of noise coming from this fan, then you know that maybe the blades are damaged. So if you have a fan like this in your concentrator, then you know that the air compressor is not receiving adequate cool air for it to be kept at good temperatures. So make sure that the fan is working fine. And also, if you have a fan that looks okay, but then it is not running, then you can check the voltage from the PCB board, from the PC board. So you disconnect the fan, and then you check for voltages from the PCB. Make sure you're checking the rating of the fan, because the other fan run under direct current, while other fans run under alternating current. So make sure that even when you're replacing the fan with a new one, you should also make sure that you have cross-checked whether it is a DC fan or an AC fan. So reaching this far, this marks the end of our presentation today. So we have covered environmental factors, user factors, and finally we have also looked at machine factors that contribute to low oxygen purity in oxygen concentrators. Right now, I'll hand over to the host for questions and comments. Thank you very much.
Thank you very much, Foster and the team, for that wonderful presentation. Indeed, there are a lot of factors that contribute to low oxygen purity in oxygen concentrators, from user factors, environmental factors, to machine factors. So right now, I will open the floor for questions and comments. So feel free to raise your hand or type the question in the chat, and I'll make sure that I give you a chance to speak so that you can ask your question freely. I can see we already have a number of hands. I think we have Good Luck Oboro and Akanyijuka. I think Good Luck can go first, and then we'll go with Abiola secondly. So Good Luck, you can go ahead, you can unmute and ask your question.
All right, thank you very much for the wonderful presentation. It's very interesting, quite in-depth. My question goes like this. One, when you put on the oxygen concentrator, did you off it immediately, or it takes, like, how long can you off the oxygen concentrator when it's on? Then secondly, this accumulator pressure test, how do we perform the accumulator pressure test on the oxygen concentrator?
All right, thank you very much. So I'm just going to repeat the questions just to make sure that we got you clearly. So the first question is about how many minutes you're supposed to wait after you've switched on the concentrator to ensure that you're giving high oxygen to the patient, right?
Yes.
And the next question is how to perform the pressure test on the oxygen tank, also known as the... All right.
Yes.
All right, those are the two questions. I think now I'll open the floor to the engineers to take the questions.
Thank you. Good luck for that question. I'm going to reply to your first question, which I believe you asked how long should you wait, or how long does it take for basically the purity to build up when you turn on an oxygen concentrator? Well,
Yes, sir.
typically, you are supposed to wait for 5 minutes. That is basically the standard period that it takes for an oxygen concentrator to actually build up to its optimal purity level. So I would say 5 minutes is the recommended time for you to wait for the optimal buildup of oxygen purity in an oxygen concentrator. I hope that answers your question.
And again, there was this I just forgot this question. There was this conversation in my office where the matron was, querying one of her junior staff that why will you be using the concentrator for like 24 hours? So I want to know the ideal time. Is it 24 hours? How long do we run the concentrators to maintain that maximum pressure or oxygen purity?
All right, thank you for that question as well. I think we'll respond to the second question and then to this one before we move on to the next person. So I can see there's a hand by Foster. Maybe Foster, you want to take that?
All right. Thank you very much for that question. So you're asking how we perform accumulator pressure tests. So to perform this test, there are usually two ways. So the other models, they have a port, a small port on the accumulator tank, which is known as an accumulator pressure testing point. So it's a very small port. You might need to connect very small tubes for you to run the test. So what you do is you remove the cover that is usually there. There is usually a small tube with the top cover that is placed there for safety reasons. So you remove that cap and you connect your tube that is connecting to a pressure regulator. So that is the easier way that you can run the test. You just connect a pressure regulator to a port that is placed on the accumulator tank. Then you should be getting readings from 20 to 30 psi on the pressure gauge. That is how you run the accumulator pressure test. The other way is connecting a pressure gauge to what is known as a manifold. So there is a connection of pipes that are coming from the sieve beds before you connect to the accumulator tank. So there are pipes. There are a number of connections that are there, and you can disconnect one tube that is going to one sieve bed, and you connect your pressure gauge. So you still have continuous flow of air from one sieve bed to the accumulator tank, and from the other sieve bed to the pressure gauge. So that is another testing point that you can connect your pressure gauge. You don't want to connect the pressure gauge directly to one sieve bed because you have pressures just continuously flowing because you have closed the path of oxygen to the accumulator tank. So you make sure that there is still continuous flow. There is no closed flow for the air. So you can connect the pressure gauge on the manifold or on the accumulator tank itself. I don't know if that answers your question.
Oh, yes, it answers. Then, sorry, Then I don't know if the gauge is beyond 20 or 30 psi or below 30 psi. What do you do?
Okay, so if you are getting pressures above 30 psis, that might be an issue with the valve, that the valve is not closing in time. So you have one seatbed being overpressurized. So you can compare the values with the other seatbed. If you're getting lower values on one seatbed and higher values on the other seatbed, that means the system is not opening equally. So you have one seatbed being overpressurized while the other one is being pressurized not adequately. So you might consider checking the control valve. Yeah, and where you are having less values, that means there might be leakages in the system. So just also check the leakages in the system. If you're still getting low values, then you need to also check the integrity of the air compressor, because all these pressures are coming from the air compressor. Just following the steps that we have discussed today.
Okay, thank you. Then how long? Sorry, how long can we run the concentrator? Is it for 24 hours or so?
So concentrators are supposed to run for 24 hours. You just have to, if you have an oxygen analyzer, you just have to make sure that you're continuously checking the oxygen purity as they are running to make sure that it's still performing at the maximum, optimum recommended oxygen purity, but they can run for 24 hours without stopping. I hope that answers your question. Good luck.
Yes.
Great. Now we're going to move on to, I think there's another hand by Abiola. I hope I'm pronouncing that right, but you can go off mute and ask the question.
Yes. Thank you very much, team. My name is Abiola, and from we are working on a project to improve the reliability and the efficiency of an oxygen concentrator in low resource settings. So my question will go to the team, because what we are seeing is some of the things we could do, but then the team didn't talk about some of the innovations we could do. Because my team had embarked on making a filter, but then we found some of the loopholes within the filter, and then we are concentrating on some other project. So I would like to request the team to give me more highlight about how we can some of the innovations and we can make to increase the reliability of an oxygen concentrator. Thank you very much.
Thank you for that question. The floor is open to the open work engineers to give suggestions on innovations related to oxygen concentrators to ensure that you make improvements in the performance.
All right. Thank you very much, Abiola, for that point. So under Open O2 as well as Oxygen Alliance, there are several things that we are doing just to improve the efficiency of oxygen concentrators. I'll just mention, I think, one thing just in passing because we are running out of time. But so one of the important part of an oxygen concentrator is the air compressor. So the compressors that are inside the oxygen concentrators are different models. So one innovation that is currently being done under Open O2 is the use of BLDC motors. So these are brushless DC motors instead of using the AC motors that are inside the air compressor. So these are efficient air compressors. They don't break so easily, and they're also running under high performance. So the incorporation of these BLDC motors in the oxygen concentrators will greatly improve the performance of oxygen concentrators that we have right now. So this is one of the innovations that we are doing under Open O2 as well as the Oxygen Alliance to improve the efficiency of oxygen concentrators. So there are several things that we have done. One of the greatest things that we are also doing as OpenO2 is the zeolite regeneration. So we also did a talk on this one. So this is an innovation that we want to reuse the zeolite that we have in the oxygen concentrators. So instead of us buying new pairs of sieve beds or also procuring new sieve material, we are using different systems to regenerate or to reuse the zeolite that is already in the oxygen concentrators. So there's several things that we are doing as OpenO2 just to improve the efficiency of these oxygen concentrators.
Thank you very much, Foster. And Abiola, you can also visit the OpenO2 website. There are also a number of, there's information concerning all the innovative activities that are happening at OpenO2. So you can also have a look at the website and see if there's anything that can help you. We'll just take one more question because of time. So Christine, I see you have raised your hand. Feel free to go off mute and ask your question.
Okay, good afternoon, everyone. So I have a question. When you're refilling the zeolite, in a scenario where you need to refill the zeolite, is there a specific pressure that you should maintain in the sieve beds when you're closing them up after refilling? And why I ask that is to know whether it's something that can be done locally or it has to be done at a manufacturer level.
Thank you for the question, Christine. Any of the engineers can take up the question.
All right. Thank you very much, Christine. So when we are refilling the sieve beds, what we mostly check are the leakages. So we do a sieve bed leakage test. So we also did a video on the sieve bed pressure test. You can watch it on our Oxygen Alliance channel. So basically what we do is we connect the sieve bed that you have refilled with zeolite to an air compressor, and you set it at 30 psi. And then using certified detection solution, leak detection solution, you check for leakages around your sieve bed. So if you are not getting any bubbles from all the leakage potential points, then you know that after you put the sieve bed inside the concentrator, you won't have any leakages or you won't have any parts popping out. So the test that we run is the leakage test on the sieve beds using a compressor and a pressure gauge connected at the other end of the sieve bed. So I think a link can be pasted in the chat for you just to check how we do the pressure test of the sieve beds. You can just follow the link and watch the testing video.
Thank you.
Thank you very much, Pastor. Jerry, maybe just go ahead before we finalize the call.
Thank you, Aubrey. And just to add to Foster's comment, Christine, your question was about the zeolite using the spring. So it's critical that the spring is in there. What we do when we put the zeolite in there is we vibrate it. And when we vibrate it, it sort of compacts itself. So if we fill the zeolite right to the top of the sieve bed and then we vibrate it, it drops almost 2 centimeters because it compacts itself. From there, we put the cover on, the spring in, and then we compress it in a special jig that we've made so that you can put the screws back in or the clip. So it's very critical that you have that compression on that spring. You want to take that spring length and almost cut it, reduce it to half of the length in order to get the pressure that you need to keep the zeolite compacted. So I think the video that has been posted, it should show all of these different components as well. But you were asking, is it possible to do it in the field or does it have to be done by the manufacturer? we have done well over 1,000 sieve bed refills, and it works perfectly as long as you make sure that you get the right amount of zeolite in there and you compress it properly. So for each different model of sieve bed, we keep track of the height of the sieve of the zeolite in there in terms of how many millimeters below the end of the bed the zeolite should be, and that way we know when we put it back together, it's going to perform nicely. And then, as Foster says, we follow that with a pressure test just to make sure that there's no leakages.
Thank you so much. Thank you so much for that elaborative answer. And I'll also go and check on your YouTube channel. Thanks for sharing the link.
Thank you, Christine. You can also reach out to the Oxygen Alliance if you need any more clarification. The engineers are always happy to help. We'll take one more question from Good Luck, and then we'll finalize the course. So Good Luck, go ahead.
So please, how do we get a new compressor? If you're working on the oxygen concentrator, like you want to change the compressor, how do we get a new compressor? And again, how do we get the replacement for the valve, the solenoid valve?
Thank you for that question. Jerry, you can go ahead.
I'll respond on the compressor one. Good Luck. Currently, we maintain about 3,000 concentrators in Malawi, and I don't think we've ever had to change a compressor. We just changed the parts that wear, and these are what we call the cups and the sleeves. I think it was shown in an earlier slide. Maybe you could just go back to that slide, whoever's controlling the slide, so it's visible. And these spare parts are readily available. You do not need to buy them from the manufacturer of the concentrator. You do not need to buy them from the manufacturer of the compressor. They're available from third-party vendors, and they're not expensive. I think less than $20 for a pair of cups and a pair of sleeves. And then within 30 or 40 minutes, you can replace them, and the compressor's running with almost new performance. I don't know whether we can post a link for the compressor overhaul. That should have been one of the early videos that we did. But it's all on the Oxygen Alliance website anyway. So it's step-by-step instructions, all the tools that you need in order to do it, and so on. Virtually all the compressors are serviceable in this way. There are very few that are not serviceable. The second question I think it's just a matter of contacting the manufacturer on that, because they are very specific to those particular models and brands of concentrator.
All right. Thank you very much, Jerry. I hope that answers your question. Good Luck.
Yes, sir. Yeah.
All right, great. So this marks the end of the call. Thank you to the OpenO2 engineers for the wonderful presentation. It has been an educative session. For all further questions, you can also email us at info@oxygenalliance.org. Don't forget to check the videos on seedbed refilling and seedbed regeneration. They are all on the Oxygen Alliance website and also on the YouTube channel. So thank you for attending the call once again. Until next time, it's goodbye.